Okay, so now we will discuss about standard. So it is also known by ideal or perfect gas equation. So we have just seen in earlier equations that P is directly proportional to T, and also we have seen V was directly proportional to T and pressure was inversely proportional to the volume. So combining all these three conditions, we got the value that PV is directly proportional to T, or we can say PV is equals to nRT. So this equation we have got by combining Boyle's and Charles' law, where N is the number of moles contained in the given gas and R is universal gas constant. So if let us consider that there are 1 mole, so PV is equals to RT. So for 1 gram of the gas, or this could be considered, where capital M is the molecular weight, MB the molecular weight, then PV is equals to R by M T, and this R by M could be written as small r. So this is a gas constant for 1 gram. Now let us move on to the universal gas constant. Universal gas constant, this the value of R. So since PV is equals to nRT, so we can get the value is equals R is equals to PV by NT, means pressure into volume into upon number of moles into temperature. So this PV we have already discussed in our previous videos that this is work done, and this can be written as NT. So this universal gas constant tells about the work done per unit temperature based on the number of moles of gas. So the SI unit of this universal gas constant B, work done, is joule, number of moles, so mole, and temperature is Kelvin. So this can be written as joule per mole per Kelvin. And what is the numerical value by this? Considering for 1 mole, let us talk about the numerical value. How could we obtain the numerical value of R? Considering 1 mole at STP, standard temperature and pressure. So at STP, volume is equals to 22.4 liters. Temperature is 273 and pressure is 0.76 meter, or if could be 760 of mercury column. So standardizing, so volume could be written as this: 22.4 liter can be converted into meter cube minus 3 meter cube, and pressure will be written as H rho g. So this is the height of a mercury column. So height and pressure is equals to H rho g. H rho of mercury could be 13.6 and g is 9.8. So putting all this value in the above equation, in this we get the value R is equals to 0.76 we get the value on calculating this to be R is equals to 8.31 joule per mole per Kelvin. So this is what in SI system the value of R becomes, and similarly if all the things are calculated in terms of CGS unit, so in CGS system R is equals to 1.98, so joule becomes calorie per mole per degree Celsius. So this is in CGS system. So now we will plot a graph between the parameters of ideal gas and a normal gas. So first let this be P atm atmosphere and this be PV by NT. So for the value, obviously this value is nothing but R. So what do we get? That at certain value, let it be 0, 100, 200, 3, 4, 5 and so on. And let this be 1, 2, 3, 4, 5, 6, 7, 8, 9. So as per this given value, R value is nearly equal to 8.31, means this could be the value of R. And since it is a constant, so it is not changing. So this is for ideal gas. But as we see for different gases at different temperature, what do we observe? For this one is temperature so this type of graph we obtain. This is for T1, T2 and T3. So there are three different temperatures on which the gases are being observed, where T1 is more than T2 and which is the temperature T1 is highest among all the three. So this kind of behavior is observed. And if we could talk about other parameters also, that is So ideal gas could be this kind. This is for ideal gas. So this is at temperature T1. So when the real gas comes at the same temperature, it behaves somewhat like this. So this is for real gas at T1. And similarly, at any different temperature T2, the gas equation will be like this. This is for ideal gas, but at the same temperature, the behavior of the real gas would be like this. So this is at T2. So you can see the difference between ideal and real conditions when the parameters is observed as volume and pressure. Next we will discuss about volume and temperature. So for ideal condition, this is your ideal condition. At any pressure P1, let it be P1, since in this pressure is kept constant. So the real condition would be like this. And suppose if we are observing some other pressure, so slope gives you the value of pressure at what pressure does we are observing the things. So we can see again the deviation at P2. So this clearly says about the difference in parameters and behavior of the perfect gas and real gas. Okay, so why do we observe that initially the conditions were similar, but afterwards we have seen the deviations? So at these points we have similar conditions like an ideal gas, but we can see the deviations here. So why do this occurs that at normal or high temperature and pressure, we can say at low pressure and high temperature, the gases behave almost likely as a ideal gas. But as the temperature decreases and pressure increases, the behavior, the interaction between the molecules is clearly observed. Why? Because we have considered that ideal gas will have no force of attraction or repulsion. So, when pressure is increased and temperature is decreased, the molecular interaction begins, and therefore it deviates the performance and behavior of the normal gas. Okay, so let us move on to the postulates of and assumptions of kinetic theory of gases.